Quantum mechanics is the area of physics that deals with the behavior of atoms and the particles on microscopic scales. Since its inception, the many counterintuitive aspects and results of quantum mechanics have provoked strong philosophical debates and many interpretations.
The 1920s was the birth of quantum physics. You can't get crazier than quantum physics. Oh my gosh, particles pop in and out of existence. You try to measure it and it's not there anymore, but you saw it there a moment ago. And it was intriguing. Once again, it was the physicist following, the bouncing ball. Weird, crazy things were going on inside the atom. That was basic science, which at the time, surely there were people who say, what are you doing? I don't understand it. Why? But we had people who were curious about the nature of the world, and they pursued it, and they were allowed to. 50 years later, we would see the birth of the information technology revolution.
The word quantum derives from the Latin word for how much. In a nutshell, it looks at objects in terms of probability as opposed to certainty. In quantum mechanics, there is no such thing as absolute certainty when looking for something. This phenomenon is known as uncertainty principle and was introduced first in 1927 by the German physicist Werner Heisenberg.
You ever, I don't know if this still happen, a quarter spills out of your pants pocket on the back seat of a car, and it's there in the wedge between the bottom and the back seat, and so you try to reach in to get it, and the act of reaching for the coin makes the coin move farther away from you. The act of reaching for it just slides down even further. That's not your mind making that happen. It's the act of the measurement that is affecting what it is you're trying to measure. And this was discovered in quantum physics, and to the point where it's the Heisenberg uncertainty principle. It's one of the basic foundations of all of quantum physics.
Heisenberg realized that one implication of quantum physics is that the act of measurement always disturbs the object measured. The uncertainty principle states that there is some inherent limit on how precisely we can simultaneously measure a particle's velocity and its position. If the uncertainty on position is small, then the uncertainty on momentum is large, and vice versa. What we observe in the world around us is not always what it seems. Classical physics, which dominates our current understanding, treats phenomena as spread out in time and space. Real-life examples of quantum physics have expanded the horizons of modern science. As Tyson emphasizes, the whole computer world is based on the principle of quantum physics. We are able to manipulate the electrical properties of silicon only because we can study the wave nature of electrons.
That's information moving that requires quantum physics. No part of the modern economy isn't touched, because information technology requires quantum physics. In the design, in the creation of data, in the acquisition, the storage, the dissemination of information. That's why it's the IT revolution. It's not a computer revolution. Computers is there. It's all about what we're doing with information. It's no longer on a printed page, here's the information. No.
Let's look at some additional examples of quantum mechanics in everyday life. Lasers and telecommunications. The operation of a laser is based on the quantum mechanical process of stimulated emission. Anytime you use a laser, whether indirectly by making a phone call or directly by scanning a label on your groceries, you're making practical use of quantum physics. The principles of quantum mechanics have also found their application in cryptography, which allows secure transmission of information from one place to another without being intercepted. Quantum communication is another key technology that can guarantee the information security of the next global communication networks. The recent rapid growth of satellite constellation has provided impetus for the development of high-capacity laser communication in space. The work carried out by researchers at the National Institute of Information and Communications Technology in Japan have demonstrated laser communications between a microsatellite and a ground station while using the quantum nature of photons to secure the data being transmitted. Another satellite technology that derives from the use of quantum mechanics is the Global Positioning System, GPS. GPS is able to tell you exactly where you are thanks to the atomic clocks aboard satellites orbiting Earth, which are set by ground control stations and synchronize themselves through signals. Every satellite is equipped with an atomic clock. Some other examples of using the underlying principles of quantum physics include fluorescent light, magnetic resonance imaging, and your toaster. Our daily routines are often governed by technology that is directly related to quantum physics. Thus, our lives rest upon these fundamental scientific discoveries. However, it is worth noting that humans are not the only species that utilize quantum mechanics. A wide range of biological processes rely on quantum physics to operate. A perplexing property of quantum mechanics could be allowing birds to see and navigate the planet's magnetic fields. 1/5 of the Earth's 10,000 bird species migrate over great distances, crossing seemingly insurmountable obstacles as they follow the seasons from one place to another. Classic physics suggests that navigating such long distances should be impossible for any organism, with the feat made doubly difficult by the Earth's turbulent magnetic fields that threaten to throw a bird off course. A team of physicists at the University of California have discovered that several species of bird may be able to see the Earth's magnetic field due to quantum entanglement. Quantum entanglement is a hard concept to understand because it is a counterintuitive physical phenomenon. Einstein referred to it as spooky action at a distance. It occurs when a pair of particles is generated, interact, or share spatial proximity in a way such that the quantum state of each particle of the pair or group cannot be described independently of the state of the others.
So it is true, and this bothered Einstein, one of the many reasons he didn't buy quantum mechanics, because of this spooky action at a distance. It is true that I can do what's called entanglement. I can entangle two particles like two electrons or two photons, create them in a very special quantum mechanical state, and then I can separate them from here to Alpha Centauri. And then let's say I take two electrons and I create them in states, so one is spin up and one is spin down. Actually, they have opposite spins. It turns out they're spinning in all directions at the same time. Now I measure this one, and I find out it's spinning over here. It immediately makes this one spin that way. Or at least that one will be measured to be spinning that way. Immediately. So isn't that information traveling faster than light? I mean, it's instantaneous. I do this measurement here, instantaneously that other one collapses into that state. Before I made the measurement, they were both spinning in all directions at the same time. I measure this one, suddenly, boom, I find it's that direction. That makes this one go in that direction. Well, it sounds like information faster than light, but it turns out it's not. No information is transferred in that.
Quantum effects are not only confined to the atomic scale. For more than 25 years, physicists have used an exotic state of matter made from ultra-cold atoms to probe quantum behavior at the macroscopic scale. Some examples of macroscopic quantum effects are superconductivity, superfluidity, and Bose-Einstein condensates. Superconductivity is the phenomenon in which certain materials conduct electricity with zero resistance and expel magnetic fields. Superconductors have an interesting property that the resistance drops abruptly to zero when the material is cooled below a characteristic temperature.
This weird aspect of the total resistance going to zero, it took 50 years for this to be understood, more than 50 years almost. And it's a weird property of quantum mechanics. The property is that somehow, it turns out in certain materials, electrons which normally repel, in certain materials, because of the property of materials, they actually attract. And they bind together and they collapse into a single quantum mechanical state. If you put a magnet above a superconductor, the magnet will float. Why is that? Well, it turns out magnetic fields can't permeate a superconductor. So they cancel that magnetic field. They repel that magnetic field.
Superfluidity is another quantum mechanical phenomenon in which a liquid loses all viscosity and flows with absolutely no friction and without any loss of kinetic energy. Bose-Einstein condensates, also called the fifth state of matter, is typically formed when a gas of bosons at low densities is cooled to temperatures very close to absolute zero. Under such conditions, a large fraction of bosons could occupy the lowest quantum state, at which point microscopic quantum mechanical phenomena, particularly wave function interference, become apparent macroscopically. Physicists behind NASA's Cold Atom Lab, which began operating in the International Space Station in 2018, have shown that the laboratory can successfully exploit the microgravity of space in ways that allow scientists to create phenomena that would be impossible on Earth. The facility is on track to become the coldest place known in the universe. Although the first quantum phenomena were observed more than a century ago, scientists are still learning about this realm of our universe. More on that in another video. Thanks for watching. Did you like this video? Then show your support by liking, subscribing, and ringing the bell to never miss videos like this.